Welcome back. So in the last video, we looked at the mechanics of CNN, convolutional neural networks, like how filter strides and pooling, or how pooling allows an AI to see spatial patterns. And now for this video, we're going to look a little bit more about the history. So between 2012 and 2015, kind of a 4-year revolution completely reshaped computer vision. We're going to examine the 4 legendary architectures that drove this transformation, understand the mathematical breakthroughs each one introduced, and see how they brought us the modern era of deep learning. So let's start with 2012 with ImageNet competition, the World Cup of computer vision, basically, where AI attempts to classify over 1 million images into 1,000 different categories. A network called AlexNet entered the field and absolutely crushed the competition, cutting the error rate nearly in half and kicking off the deep learning boom. Now, why was it so much better? 3 reasons. First, it was the first major architecture to abandon old school sigmoid and ton functions in favor of ReLU, as mentioned in earlier videos. So this allowed it to train several times faster without gradients vanishing. Second, it used massive data augmentation, like randomly cropping, flipping, and altering the training images so the network couldn't just memorize the data. Third, and most importantly, it was the first network designed to run massively parallel processing power of gaming GPUs. Now, by 2014, researchers were trying to figure out how to make networks, deeper without exploding the computational costs. A team at Oxford introduced VGGNet, which proved a fundamental design rule. Always stack small filters instead of using large ones. Before VGG, researchers often used like large 5 by 5 or 7 by 7 filters to capture wide patterns. VGG produced a second two 3 by 3 filters cover the exact same spatial area as a single 5 by 5 filter, but with two massive advantages. First, it uses significantly fewer parameters, 18 weights instead of 25. Second, because the data passes through 2 layers instead of one, you get to apply 2 ReLU activation functions instead of one, giving your model much more nonlinear representation power. Now, the same year, we're still in 2014, Google released GoogleNet with a capital LE in Google, which asks a clever question. Instead of just stacking layers deeper, why not go wider? They designed the Inception module. When analyzing an image, you don't always know if the feature you're looking at, looking for is tiny or huge. So an Inception model runs a 1 by 1, a 3 by 3, and a 5 by 5 filter all at the exact same time, stacks the results together, and lets the network decide which scale works best. But there's a catch. Running all those filters at once is computationally brutal. To solve this, Google popularized the 1 by 1 convolution as a bottleneck. By running a 1 by 1 filter before a larger 3 by 3 filter, you effectively compress the depth of your feature maps, stripping away redundant information and slashing computation costs while keeping the spatial patterns intact. Now, by 2015, researchers hit a brick wall called degradation problem. So as networks grew past 20 or 30 layers, their accuracy didn't just plateau, it actually got worse. This wasn't just overfitting, right? Optimizing itself was breaking down because passing data through endless layers scrambled the original signal. Enter ResNet, the undisputed MVP of modern computer vision. ResNet solved this one with one deceptively simple addition: the residual or skip connection. Instead of forcing data to crawl through every single layer, ResNet added a wire that skips over the layers, sending the original input, X, directly to the output. Now the math becomes, X, H, I think I have it right here. This is like basically the formula. So this skips connection as an information superhighway. If a deep layer isn't useful, the network just pushes its way to zero and relies on the clean, uninterrupted signal passing through the skip connection. Overnight, ResNet allowed researchers to train with 152 layers and beyond, completely shattering existing records. Now, from AlexNet's GPU acceleration to ResNet's skip connections, these four architectures laid the mathematical blueprint for almost every visual AI we use today. But up to this point, our models have had a major blind spot. They can only process static, fixed size data. What happens when we need an AI to understand sequential data over time, like audio clips, stock prices, or just human language? So, I believe in the next video, tackling more about time and memory with recurrent neural networks.